Okay, in this video I'm going to look at how to find Laplace transforms of piecewise continuous functions. If you are watching this and you haven't looked at our videos on how to express piecewise continuous functions in terms of Heaviside functions, we strongly recommend that you do that first. We want to post a link of those videos just now. Okay, so let's start with the first one. So in A, we have got a function which is defined by 0 between t equals to 0 and 2. And then from 2 onwards, this function is given by this quadratic expression. So that's for 2 and bigger. We are going to work through this using two approaches. In the first method, we are going to use the definition of the Laplace transform. So we're just going to plug this into that integral there. So the Laplace transform of f of t is going to be equal to the integral from 0 to 2 of 0 times e to the minus st dt. So that's this bit here. Then from 2 to infinity, it's going to be t squared plus 3t plus 2e to the minus st dt. So then the first term is just going to vanish, so that one is 0. The second term, we've got a polynomial times an exponential, so we can integrate that one using tabular integration. So we're going to take the polynomial and differentiate it repeatedly to 0, and then we're going to take the exponential term and integrate it repeatedly. So here we're going to have e to the minus st. The integral of that is minus 1 over s e to the minus st. Integral of this one is 1 over s squared. And then the last one is minus 1 over s cubed. And then we are going to match them accordingly. First one onto the second one, etc. This one goes with a plus, and that one goes with a minus, etc. Again, we have got a whole video which is devoted on this method. If you're not up to speed with it, we're going to post a link of it so you can check it out. So what's going to happen is then the Laplace transform of f of t is going to be, all the terms are going to be negative, because for this one I got plus and minus here, plus and minus there. So we're going to have t squared plus 3t plus 2 over s. We're going to have 2t plus 3 over s squared. We're going to have 2 over s cubed. These are all multiplied by e to the minus st. And then this is evaluated between 0 and infinity. And the limit t goes to infinity, this whole term is going to go to 0, because that goes to 0 quicker than the n of the polynomial terms. Okay, so the only contribution is going to be from the end, lower limit end. Sorry, this is 2, not 0. So when t is equal to 2, we are going to have negative, this is going to be 2 squared, which is 4 plus 6, so that's going to be 12 over s. Then this one is going to be 4 plus 3, 7 over s squared, then 2 over s cubed. This whole thing is multiplied by e to the minus 2s. So that is going to be the Laplace transform of this function using that approach. We are now going to use the approach of expressing the function first in terms of the Heaviside functions. So I'm going to use the Heaviside function. From the videos we've done on how to express piecewise continuous functions in terms of the Heaviside function, you can see that this function is going to be 0 between 0 and 2, and then it's going to be given by that quadratic between 2 and infinity. So it's going to actually, when t is 2, this function is 12. The turning point of this function is going to be somewhere this side, on the left hand side of the origin. So this function is probably going to be something like this, going up like that there. So in terms of the Heaviside function, this is simply going to be h of t minus 2 times, of course, t squared plus 3t plus 2. However, the property that we have for Laplace transforms works better if the argument of the Heaviside function is exactly the same as the argument of the function at hand, because then we know that this is equal to that. So what it means is that we need to express this as some function of t minus 2. We can do this using two methods. We can do it algebraically, or we can do it just by writing the Taylor series of this about 2. Okay, so let's use the Taylor series then. So if we use the Taylor series, so the Taylor series says f of t about 2 is f of 2 plus t minus 2 f of 2 f prime of 2 half t minus 2 squared f double prime of 2, etc. So all we need to do here is to find f of 2, f prime of 2, f double prime of 2, etc. So if we start with f equal to t squared plus 3t plus 2, we need the derivative of this, which is 2t plus 3. The second order derivative of this is 2. The third order derivative of this is 0. So that means these are all the terms we're going to need. Then if we plug in 2 in f, we've already done this actually, it gives us 12. If we plug in 2 here, it gives us 7. We already did it in this calculation here. It's just going to be these numbers there. If we plug in 2 there, it's going to give us 2, of course. So what this is telling us is that our function is going to be 12 plus 7 into t minus 2 plus 2 over 2 t minus t squared. So then we can take this and plug it in here. Okay, so that is the Taylor series approach. We could do this algebraically as well. Okay, so algebraically, you just need to be up to speed with your completing the square. So this is how it's going to go. So f of t is t squared plus 3t plus 2. So we start with the t squared term. Now, if we convert this into t minus 2, okay, if we convert this into t minus 2, so I'm just converting this one into t minus 2. Then there are two things that will have, this will do. So these are just the terms that are there. So if you convert that into t minus 2 squared, then you will have added a minus 4t from here. So which we need, added minus 4t. So we need to subtract minus 4t, which means it's going to look like that. And then something else we'll have added is 4. So we need to subtract that. So by doing this, then these two, this is still exactly the same as that. Then, so what's going to happen is that we are now going to have t minus 2 all squared plus 7t minus 2. Then next we go to this one and write it as a t minus 2 of sorts. Okay, so it's going to be 7 into t minus 2. Let's just write it like this. Okay, so t minus 2 plus 2. And then we are going to remove brackets. When we remove brackets, we're going to write this as 7 into t minus 2, this bit, and then the other bit is going to be 14. So finally, we have got t minus 2 squared plus 7 into t minus 2 plus 12. Now you're going to notice again, of course, this is exactly the same as what we got there using the Taylor series approach. Now back to our Laplace transform. So what it means is that the Laplace transform of f of t is going to be the Laplace transform of so this is going to be the Laplace transform of h of t minus 2 into t minus 2 squared, 7 into t minus 2 plus 12. Now according to that formula there, which we wrote earlier, this one here, it's going to be e to the minus as. A is 2, so it's going to be e to the minus 2s. Then the Laplace transform of f. So for this one is just t squared. Laplace transform of t squared is 2 over s cubed. Laplace transform of t from this one is 1 over s squared, and Laplace transform of 12 is going to be 12 over s. And then you're going to notice that this is exactly the same as the one we obtained using this method. This negative shouldn't be there because this is the lower limit, so it's just positive. All right, so I think we are going to stop here with this video. We're going to continue with the other examples in the next part, which is going to be part 3. Thank you for watching. Do of course remember to subscribe to support the channel. All right, thank you.